This is Chapter 12, the oscilloscope. Section 1 is background information. This is a photograph of an oscilloscope. So digital multimeters and analog meters, they're very good at measuring DC voltages because the DC voltage is constant. Those types of meters are bench meters. They can measure AC voltages as well, but they give us the RMS value. Which again is the effective value for the same power dissipation properties as a DC circuit. And so that doesn't give us the full picture of the waveform. And so a sine wave, for example, versus a square wave can have the same RMS value, but they're obviously different waves. And so the oscilloscope allows us to actually view the waveform on a screen. And so these are several different pictures that we see here of oscilloscopes. You can see some waveforms on them. Notice there are many panel buttons, knobs, and things like that. There's also on-screen menus that we can cycle through and access. This is a picture of an oscilloscope that we actually have in the lab. It's by Tektronix. Several more here. So lots of front panel buttons. We'll see what some of those do. There's also on-screen menus that we can navigate through. The oscilloscope is very good at telling us the amplitude of a waveform, also the period of a waveform, and also the rise and fall times. For example, square waves, they look like the voltage changes from one level to another instantly, but actually that takes time to do that. So that would be the rise and fall time of a signal. They can calculate the duty cycle force. The average and the RMS values can all be calculated by an oscilloscope. All oscilloscopes use a cathode ray tube to produce the picture on the screen. And all scopes have an adjustable display that allows us to analyze the voltage, the time, the waveform, and frequency parameters of the signal. This is section 2. It's the key sections of the scope. And so here you see a generic photograph of what an oscilloscope might look like. Obviously there is the screen. We have the vertical and horizontal positioning knobs. This would be a two-channel oscilloscope, channel 1 and channel 2, so it can show two different waveforms at the same time. The vertical positions will move those waveforms up and down on the screen, and the horizontal can move it left and right. Also notice there are volts per division knobs here. These are essentially zoom knobs. These allow us to zoom in and out on the waveform in the vertical direction, so it stretches it vertically. We also have the seconds per division knob. This is essentially a zoom knob that allows us to zoom in horizontally. This is a diagram of what a cathode ray tube might look like. So essentially what's happening here is electrons are being fired through this vacuum tube. And when those electrons are being fired, when they hit the screen has phosphorus in it, and it illuminates a sort of a yellowish greenish color, and that produces the image that we see on the screen. And so what you're seeing here are vertical deflection plates and horizontal deflection plates. Essentially what's happening as electrons are being shot through this tube, if we apply a voltage to these plates, and let's say the top plate is positive and the bottom plate is negative, as an electron is passing through here, it's going to be attracted to the positive plate. That's going to cause the electron to be deflected and put a mark on the screen at a higher position. And if we reverse the polarity of the plates, then the electrons will be deflected downward and make a dot lower on the screen. Also, if the voltage on the plates is small, the deflection amount will be relatively small, and the beam will only move up or down slightly. But if we increase the voltage to a higher value, the beam will deflect more, and we could put a dot very high or very low on the screen. And so the vertical deflection plates deflect that electron beam up and down. We also have horizontal deflection plates. These are going to deflect the beam to the left and to the right. And so with no voltage applied to the plates, as the electron beam is coming through the tube, we would essentially see a dot right in the center of the screen. That's what you see here in figure A. If the top plate was positive and the bottom plate was negative by some DC source, the electron beam would be deflected upward. Those electrons would be attracted to the positive plate. Same thing if we apply a DC voltage to the horizontal plates. This will move the dot to the left or to the right, in this example to the right. And here, if we apply voltages to both the vertical and horizontal plates, it's going to pull it not only down but also to the right. And so we can move this dot diagonally as well. And so it will appear in the lower right hand corner of the screen. If we were to apply a AC signal to the deflection plates, When the AC signal is high, the top plate is positive, the bottom plate is negative, and the electron beam is deflected upwards. And when the sine wave is low, now the bottom plate is positive, the upper plate is negative, and the electron beam will be deflected downward. Now if the frequency of the sine wave was slow enough, we would see the dot moving up and down with the same frequency as the sine wave. And if the sine wave was very fast, if the frequency was high enough, we would just see a line on the screen because it's moving faster than our eye could process. Same thing for the horizontal plates. If we apply sine wave to the horizontal plates, we'll see a horizontal line. And if we apply sine waves to both plates at the same time, we will see a diagonal line. And so the horizontal plates, under most circumstances, have a sawtooth wave applied to them. And so what this causes to happen is, as the voltage rises, it actually starts off as a negative value, at some point in time crosses 0 where there's no voltage, and then increases to some positive value. As this voltage is rising gradually, this is going to cause the electron beam to move from one side of the screen to the other. And then the sawtooth wave very rapidly returns back to its original value. More rapidly than it took to rise, it will fall. And so the electron beam is going to move from left to right across the screen. When it reaches the right, it will reset rapidly and draw another line across the screen. This is the default setting for the oscilloscope. This sawtooth wave is generated internally. So the key sections of the scope, we have the vertical section, those deflection plates. Those deflection plates, the voltage for those vertical deflection plates comes from the signal that we're measuring. And so with the oscilloscope, we're trying to measure changing voltage values. And so that voltage value that is changing is the voltage value that we apply to those vertical deflection plates. So the input jack from the scope is connected directly to those vertical plates. It can be 1 or 2 channels. We can have up to 2 probes or leads coming from the oscilloscope, and therefore we can display 2 different waveforms on the screen at the same time. There will be vertical attenuation or vertical amplification. That enables the decreasing or increasing of the amplitude of the signal. In other words, that allows us to zoom in and out vertically. We can stretch the waveform vertically, or we can shrink it vertically. The horizontal section, it adjusts the frequency of the horizontal sweep. And so a sine wave, we can zoom in and out. We could see just one period of the sine wave on the screen, or we can zoom out and see multiple periods of the sine wave on the screen. The gain control changes the length of the horizontal trace line. Again, that's a zooming in and zooming out. There's also an external connection that enables an external signal to control the horizontal deflection plate system. And so again, by default, we apply a sawtooth wave there, but we could apply other waveforms to the horizontal plates as well if we desired. So there are synchronization controls. This synchronizes the horizontal trace and the frequency of the waveform. So if we're measuring a waveform that has a frequency of 100 Hertz, we want the sawtooth wave on the horizontal plates to also be at 100 Hertz. They need to match and be equal, or they at least need to be multiples of one another for zooming in and zooming out. But the synchronization controls can detect what the frequency of the input signal is, and then adjust the frequency of the triangular waves so that they match. And then this causes the image to appear stationary on the screen. The electron beam will trace out the same pattern on the screen over and over again, and we just see a stationary screen image on the screen when that happens. So this assumes that the waveform is periodic. As long as the waveform continues to repeat itself over and over, the image on the screen will appear to be stationary. But if the signal is not periodic, we can use external trigger sources, and this will cause only one trace of the image to appear on the screen. It will be remembered, and then it will be repeated over and over again, and then again this will produce what appears to be a stationary image. And so if it's not a periodic waveform that we're trying to view, we'll capture one period of the waveform. There may only be one period, and then that will be remembered and repeated over and over on the screen for us. This is section 3. This is combining the horizontal and vertical signals to view a waveform. And so again, here at the bottom, the voltage applied to the horizontal deflection plates is going to be a sawtooth wave. And notice that the rise time, it takes a long time for the signal to rise relatively, and just a very short time for the signal to fall. and so this is going to cause the horizontal tracing of the signal. And at the same time that the beam is tracking from left to right, our signal that we're actually measuring is being applied to the vertical plates. And so as the horizontal deflection plates move the beam from left to right, at the same time the signal is causing the beam to move up and down. And so that draws this signal on the screen for us. And notice that the frequency of the waveform that we're measuring needs to match the frequency of the sawtooth wave on the horizontal plates. They either need to be equal or they can be multiples of one another. So here you can see that the frequency of the waveform being measured is 120 Hertz. We can have the frequency of the sawtooth wave be only 60 Hertz, half of that, right, as long as they're even multiples. And that way 2 complete periods of the sine wave now appear on the screen rather than just one. If they matched perfectly, we would only see 1 period of the waveform. If it's a multiple of 2, we would see 2. If it was a multiple of 3, we would see 3 complete periods. Here we're applying the standard sawtooth wave again to the horizontal plates, sawtooth wave to the vertical plates, and so what we see is this sawtooth wave appear on the screen. If we apply a square wave to the vertical plates, sawtooth to the horizontal, we will see a square wave on the screen. So whatever signal is being applied to the vertical plates essentially is the waveform that we will see on the screen. This is section 4. It's measuring voltage and determining current with the scope. So the scope has a volts per division knob on it that can be turned. This is essentially the zoom and the vertical direction. And so the screen of the oscilloscope is divided up into what we call divisions, and these divisions represent a certain amount of voltage, and that voltage that is being represented is determined by this knob. And so here we see a waveform on the screen. The knob is set to 0.1 volts per division. That means that every square in the vertical direction on the screen represents 0.1 volts. And so here you can see this is the 0 line. And so the peak voltage of the waveform would be 1, 2, 3 divisions, and each division is worth 0.1 volts. And so the peak voltage is 0.3 volts, and also the negative peak voltage is also 0.3 volts. Now if we were to switch this to say 1 volt per division, now every square would represent 1 volt, right? So from here to here would be 1 volt. That's going to zoom out on this waveform. If we turn this knob to 1 volt, this waveform would only rise up to 0.3 volts, which now would be down here somewhere, return back to 0, and sink down to negative 3 volts right about here somewhere. So if each division is worth 1 volt, 0.3 volts, which is the magnitude of our waveform, is going to be somewhere less than 1 division. And so that's essentially going to zoom us out. This is an image of the scope probe. This is what the lead looks like. It has this connector that you push onto the port and then you turn it to lock it into place. And wherever you connect this probe to the circuit is the waveform that you'll be measuring. This is section 5. It's using the scope for phase comparison. We can view 2 waveforms on the oscilloscope at the same time, and they may not necessarily in phase. And so one complete period of either of the waveforms is 360 degrees, right? That's one complete oscillation. And the difference between the 2 signals, that is something less than 360 degrees. So the ratio of x over y is going to be equal to the ratio of whatever this angle is represented as here, 60 degrees. And so we can solve for the angle of the difference in phase between 2 waveforms by taking x, which is the number of divisions between the waveforms, divided by y, which is the total number of divisions of one complete period of one of the waveforms, and then multiply 360. And we will get an answer in degrees, and that will tell us the angle between the 2 waveforms. This is section 6. It's determining frequency with the scope. The period of the waveform is going to be the number of divisions that one complete period occupies times the value of time per division setting of the time per division knob. And so again, each division in the horizontal represents a certain amount of time, which can be set with a dial on the front of the oscilloscope. Whatever that dial is set to, we can multiply by the number of divisions of a complete period, and that will tell us the period of the waveform. That answer will come out in seconds. We can calculate the frequency once we know the period. 1 divided by the period is the frequency. And so here we see a waveform on the oscilloscope screen. Notice that there are 10 divisions in the horizontal direction across the oscilloscope. And so this waveform occupies all 10 of those divisions. So from the start of the waveform to the end in the horizontal direction is 10 divisions. And each division is representative of 5 milliseconds. And so the period of this waveform would be 5, 10, 15, 20, 25, 30, 35, 40, 45, 50 milliseconds. And so if each division is 5 milliseconds and there are 10 divisions altogether, 10 times 5 milliseconds is 50 milliseconds. The period of this waveform would be 50 milliseconds. So determining frequency with the scope. Assume that the seconds per division control is set to 0.1 seconds per division. So each horizontal division on the oscilloscope screen is representing 100 milliseconds. And so also assume that the scope pattern shows exactly 4 cycles of the signal to be measured across the 10 horizontal divisions. And so in this example we only see 1 cycle. And so in the example we're reading now, it's stating that there's going to be 4 complete oscillations across the screen. And so if there are 10 divisions across the screen and we are seeing 4 cycles, each cycle must take up 2.5 divisions. And each of those divisions is worth 0.1 seconds per division. And so if you multiply 2.5 divisions for each cycle times 0.1 seconds per division, you would get 0.1 times 2.5 is 250 milliseconds. The period of that waveform must be 250 milliseconds. And we can determine the frequency by taking 1 divided by 250 milliseconds, which is going to be 4 hertz. So in other words, we see 4 complete cycles every second. Assume the seconds per division control is set to the... This example says assume the seconds per division control is set to 50 microseconds per division. This time the pattern shows exactly 10 cycles of the signal under test. So we see 10 complete oscillations of the sine wave across the screen, and there's 10 divisions. So each cycle must occupy 1 division. Each division is worth 50 microseconds. So the period of the signal is going to be 50 microseconds. And if we want to know the frequency, we divide 1 by the period. So 1 divided by 50 microseconds is going to be 20 kilohertz. So the frequency is 20 kilohertz. This is an image of the oscilloscope from the lab. Here you see a sine wave, and you can see down here at the bottom in the left it says that channel 1 is set to 200 millivolts. That is the millivolts per division, or the volts per division setting. You can adjust that here. If you turn this knob for channel 1, this is going to zoom the image in and out in the vertical direction. The seconds per division knob is the same for both channels. There's only one. That will zoom in and out on the horizontal axis. And so in this example, if each division is worth 200 millivolts, we would need to count how many divisions it was from the bottom peak all the way up to the top peak, and then we can divide that by 2, and that will tell us the peak number of divisions. We can determine the peak voltage. And so here you see that the oscilloscope screen is divided into squares. Each square is 1 division, and each square is also divided up into smaller divisions. There's 5 altogether, so each small tick that makes up the square is worth 0.2 of a division, because there's 5 altogether. And so if you count the total vertical divisions, I'll start here at the nearest whole division. It's going to be 1, 2, 3, 4 full divisions, plus whatever fraction is here. And so this looks like maybe about 2 ticks, so that's about 0.4. And up here it's maybe about 2.5 ticks, so that's going to be another 0.5. So 0.9 from the fraction here, plus 4 total divisions is about 4.9 divisions. And so if we take the number of divisions, which is 4.9, and we multiply by the volts per division setting, which is 0.2, we get a peak value of about 980 millivolts. And you can see the on-screen menus here. It says that the peak-to-peak voltage is about 960. So my estimate in counting the number of divisions was slightly off, but that doesn't matter because the oscilloscope actually tells me the peak-to-peak voltage is 960 millivolts. I could divide this by 2 and get the peak voltage as well. The seconds per division setting is 250 microseconds, And so if we count the number of divisions from one peak of the waveform to the next peak, so here you see this is pretty close to the even, right on the line. And so it's about 1, 2, 3, maybe 0.6, maybe about 3.6 divisions. And so if we take 3.6 divisions and multiply by the 250 microseconds per division, we will get a frequency of about, a period of about 900 nanoseconds, roughly. And you can see that the oscilloscope screen tells us that the period is actually 887, so it's pretty close there, not quite exact. And if we take 1 divided by 887 microseconds, we will get the frequency. And the screen also tells us that it's 1.127 kilohertz. When I divided, I got 1.127 kilohertz, and so I got the same answer. And so this is what the oscilloscope looks like. These are the settings that the channels are currently set to, along with the seconds per division setting, and we can calculate the peak-to-peak voltage or the peak voltage and the period and the frequency of the waveform just by observing the screen. The oscilloscope also does those calculations for us. This is a block diagram. This is a summary of how the oscilloscope works. We have the vertical and the horizontal deflection plates. Horizontal plates by default have the sawtooth wave applied to them. We could input an external signal to override that sawtooth wave if we wished. That's not something that we'll generally do. The actual input voltage that we're reading is tied directly to the vertical deflection plates, and so that's what draws the waveform on the screen. And this, of course, is all powered by digital electronics, which is DC power. This is section 7. It's about the function generator, and so this is an AC waveform generator. In DC circuits, we used a DC generator. It produced a DC voltage. We applied that to our circuits, and then we analyzed the circuit. The function generator is an AC generator, and so it's going to generate sine waves for us. Also, it can do triangular and square waves. We can adjust the frequency and the amplitude. This is the one that we have in the lab, and notice that there's a knob for amplitude. There's also a button right here. You can see that when the button is pressed, the amplitude will range from 0 to 2 volts peak to peak. And if the button is popped out, it will be 0 to 20 volts peak to peak. And so this button controls the range of this knob. We can select a sine wave, a triangular wave, or a square wave. And we can set the frequency with these buttons. We will pick a value that is generally close to the value that we're looking for. And so we could get 3 kilo ohms by pressing the 1K button and then turning this knob to 3.0. And so 3.0 times 1K is 3 kilo ohms. And so that'll be roughly the frequency of the signal. We could also press the 10 kilohertz. We could press the 10 kilohertz button and set the knob to 0.3, and 0.3 times 10 kilohertz again would be 3 kilohertz. So those are the two ways that we could set the frequency of the function generator.